So these set of notes are dealing with quantitative force diagrams. So before we just had qualitative force diagrams, now we're actually going to be putting numbers on them. So forces do not cause motion, they cause acceleration. So we know this by Newton's second law, sigma F equals mass times acceleration. So when you slide a book across the table, it does not come to rest because there is an absence of a force, rather because there is a presence of a force, and that force being friction. So as I stated before, Newton's second law states that forces cause acceleration. So it's the sigma F, your F net, your fun ball, however you want to say it, is equal to the mass times acceleration. And just like we've been saying in the past, you always accelerate in the direction of the unbalanced force. We have the weight equation where it's weight equals mass times g, where g is always 10. But in Newton's second law, this equation, this a value is not always 10. It's only 10 when you're calculating how much Earth is pulling on the object or if the object is in free fall. So when you go to the moon, we've talked about this in the past, your mass does not change, but your weight does. So if you stood on a scale on the moon, your weight the number on the scale would be different on the moon than on Earth, because the moon is going to pull on you less than what Earth will pull on you. Earth pulls on you with a force of 9.81 meters per second squared, versus on the moon, the acceleration is 1.67 meters per second squared. So back when we did the weight versus mass lab, we found this equation. We figured out that the weight is equal to the mass of the object times the acceleration due to gravity, which is 10. We had the Kathy and Rich example, which had the two different objects have different mass. They both were released at the exact same height at the exact same time, and they hit the ground at the exact same time. Kathy said that the force of gravity was the same on both objects. Rich said no, the heavier object had a greater force of Earth's pull. And we figured out that Rich was correct, because we saw when we graphed our data that if you increase the mass, the force of Earth's pull was greater. So things that have more mass has a greater force of gravity on them. So again, G is always going to be a constant. G is always going to be 9.81. We can round up to 10 to make our calculations a little easier on us. And since a Newton force is equal to a kilogram times meters per second squared, we always need to make sure the mass is in kilograms. So we're going to start doing some calculations and putting numbers on these force diagrams. So this example says a rightward force is applied to a 6 kilogram object to move it across a rough surface at constant velocity. So I automatically see this word constant velocity, and I think in my head my force diagram needs to be balanced. It tells me that it encounters 15 newtons of friction, and we're going to draw the force diagram and determine the gravitational force, the normal force, which again is just how much the surface is pushing perpendicular on the object, the net force, again your sigma F, your fun ball, and how much that applied force is. So here we go. So we're going to start off by drawing our force diagram. We have our dot. We have Earth pulling down on the object. So that's the force of Earth on our object. And again, this is the same thing as weight. And we calculate weight by taking the mass times the acceleration due to gravity, which is 10. So the mass was 6 times g, 10. And so Earth is pulling down with 60 newtons. Then it's on a rough surface, so the surface is going to be pushing up, assuming it's not going down into the ground, it's not coming up off the ground. The ground is going to be pushing up with the exact same amount of force that Earth pulls down. So this is the force of the surface on the object. So if you need to be balanced vertically, then the surface also needs to be pushing up with 60 newtons. So 60 newtons down cancels out with 60 newtons up. Then it says a rightward force was applied, and then if it's moving to the right at a constant velocity, friction is always the opposite direction, and it tells me that friction is 15 newtons. So if I drew these vectors this long that represented 60, obviously I'm going to be drawing a smaller vector for our friction. So that will be friction. So the friction of the surface on the object, and it tells me that that amount is 15. And if it's moving at a constant velocity, then the push also needs to equal the friction force. So it needs to be force of the push on the object also needs to be 15. So 15 newtons to the right cancels out 15 newtons left. So we are balanced vertically and we are balanced horizontally. So the gravitational force is 60 newtons. The normal force, which is just the surface, the normal force is 60 newtons. The overall net force is just 0 newtons. Because again, you are balanced vertically, 60 newtons down, cancels 60 newtons up, that equals 0. 15 newtons to the right cancels out 15 newtons to the left, overall 0. So net force equals to 0, no acceleration, constant velocity. And the applied force, again, so we were given this, so if it's constant velocity, you need to be balanced, so the push, the applied force was 15. So for this example, it says an applied force of 50 newtons is used to accelerate. So I see this word accelerate, and I automatically think that my force diagram needs to be unbalanced to an 8 kilogram object to the right across a frictional surface. The object encounters 10 newtons of friction. Draw the force diagram, determine the gravitational force, normal force, net force, and the acceleration of the object. So we will be using Newton's second law to calculate the acceleration of that object. So starting off drawing my force diagram, we always have our one non-contact force, which is Earth's pull, which is going to be down. The force of Earth on the object. And again, this is the same thing as weight. We calculate it by taking the mass times 9.81, but we'll round up to 10. So since this is a 8 kilogram object, we do 8 times 10, and we get 80 newtons. Again, usually it's going to be on the surface, so we're going to need to be balanced vertically. So this frictional surface needs to be pushing up with the exact same amount that Earth pulls down. So right there, we've already figured out the gravitational force, 80 newtons. The normal force, again, is how much the surface is pushing on the object, which is 80 newtons. And now it says that it encounters 10 newtons of friction. So friction, if it's going to the right, friction is going to be to the left. So we're going to have a very small vector here for friction, which is going to be 10. And then it also says that there was an applied force, 50 newtons to the right. So it needs to be longer than this one, but it needs to be shorter than these two vectors up. So this is the force of the push on the object, and that is 50 newtons. So to figure out our net force, we look at our force diagram. You're balanced vertically. So then we look here, I say, okay, 10 newtons to the left will cancel out 10 newtons to the right. So that amount is 10. And then you have a portion that's left over, and that portion is your net force, your fun ball, your sigma F. So if this is 10, that's 10, then the rest of this needs to be 40, because it needs to total 50 newtons. So 10 plus 40 is 50. So your net force is 40 newtons. So we can use, and when I have a net force, whenever you have acceleration, we should think of Newton's second law. And we just figured out that the net force was 40. We were given the mass in the problem, which was 8. And we can solve for the acceleration just by dividing. So our acceleration comes out to be 5 meters per second squared. All right, so our last problem, it says, in a physics lab, Kate and Rob use a hanging mass and pulley system to exert a rightward force on a 0.5 kilogram cart to accelerate it at a rate of 3.46 meters per second squared. So accelerate, our force diagram needs to be unbalanced, and they are actually giving me the acceleration value across a low friction track. If the frictional force is 0.72 newtons, draw the force diagram. And then it wants to know what is the force of the track on the cart, and then what is the force being applied rightward on the cart. So starting off drawing our force diagram, start drawing a dot. So we have always our one non-contact force, which is going to be gravity. So the force Earth on the object. This is equal to weight. Again, we just take the mass times the acceleration due to gravity. So we take 0.5 times 10, and we get 5 newtons down. It's going to stay on this track, so the track must be pushing up with the exact same amount. The force of the track on the object, which is going to be 5 newtons. And then it says there's a rightward force, so it's going to be pulled to the right, and we know friction will be in the opposite direction. So we know friction is going to be to the left. Friction of the track on the object, which is going to be 0.72. And then we know that it's accelerating to the right, so we are going to have a longer vector than friction to the right, and that's the force of the that the pulley is pulling on the mass. So I'll just say the force of the pulley on the object, and we don't know how much that is, but they did give me in the problem my acceleration value. So whenever you accelerate, you automatically should think of Newton's second law, which states sigma F equals mass times acceleration. We know it's a 0.5 kilogram object, and they told me my acceleration value, which is 3.46. So 0.5 times 3.46, that comes out to be 1.73 newtons. So that is the unbalanced portion, okay, of this vector. It's not what this is equal to. It's just the unbalanced portion. So I think most of us can agree that 0.72 newtons to the left will cancel out 0.72 newtons to the right. So that is 0.72. And the rest of this is your sigma F, which we just calculated to be 1.73. So if we add those two values together, we can get the overall force of how much the pulley is being exerted on the object, which comes out to be 2.45 newtons. And if we look, we would hope, if you can rearrange some of your drawings, this vector, this is approximately half of this. So I would hope that this vector, you can change the lengths and stuff, that this should be half of this because it's half the amount, because again, the length of the vector does matter. So we know that the force of the track on the object is the normal force, which we figured out 5 newtons based on how much Earth was pulling down, and we were given this and the acceleration, which we were able to solve for the unbalanced portion of that, which gave me this. Adding these two values together gave me the overall force of the pulley on the object.